Hi, my name is Lucia Bellino, and I'll be presenting my work on the presence of widespread hydrothermal minerals in the Eridania Basin on Mars and the implications for formation mechanism. This work was completed in conjunction with Dr. Lucia AGU at Rutgers University. With Mars only receiving 57% of the incoming solar radiation that the Earth receives, and the sun's luminosity being 20 to 30% lower during the Noachian than it is today, the question then becomes, how could Mars's surface have been warm enough to support the presence of liquid water billions of years ago? One potential method would have been through liquid water existing within a hydrothermal system, in which internal heat allows liquid water to be stable on the surface because it achieves a high enough temperature to be sustained. Hydrothermal systems are extremely important to study for a number of implications. With both the oxygen and hydrogen present within water, redox reactions are important to study within hydrothermal systems. Additionally, the internal heat that allows liquid water to be stable within hydrothermal systems are important to the geophysical and crustal evolution of the planet. With both water and heat being key ingredients for life, and hydrothermal systems often containing additional minerals like carbon or fluorine and phosphorus that are essential for life, hydrothermal systems are also very important to study for habitability and astrobiological implications. Finally, hydrothermal systems can also tell us a little bit of information about the climate of the planet even billions of years ago. One region that's really interesting to study, both for climatic implications and a number of other reasons, is the Eridania region. It's located on the boundary of Terra Serenum and Terra Cimmeria and is made of a number of interconnected basins. The scarp-bounded benches of Gorgonome chaos, the concave hypsometry of the basins, and the presence of iron-rich minerals throughout the basin indicate that the Eridania region would have once been an ice-covered sea during the Noachian. The outline of this theoretical ice-covered sea is noted in this black 1,100-meter contour line. There's also a white 700-meter contour line, as well as striped deep basin deposits. The entire theoretical sea is plotted on top of an elevation map, which has higher elevations plotted in red and orange, and lower elevations plotted in blue and green. The basin is located directly below Modum Vallis in the Gusev crater. This theoretical Eridania Sea would have been a huge reservoir of liquid water on Mars during the Noachian. In fact, if it existed, it would have contained more water than all of the other Martian lakes combined. And it also would have been about 3 times the size of the largest landlocked sea on Earth, which is the Caspian Sea, as you can see from this image from Mikulski et al. 2017. Despite the pieces of evidence that support the theory that the Eridania region was once an ice-covered sea, there's still a lot of debate about the formation environment of the Eridania region. In 2020, Leverington published a paper that claimed that the formation environment for the Eridania region was dry volcanism. One of the main pieces of evidence that Leverington pointed to make this claim was that the concentration of hydrated mineral detections outside of the Eridania region, but still within this Terra Serenum, Terra Cimmeria region, was not substantially different than the concentration of hydrated mineral detections within the actual Eridania region. And so because of this, he claimed that this was not consistent with the idea that an enormous and long-lived lake would have existed on Mars during this time. In the image on the right, we have the theoretical Eridania Sea outlined in white. The red squares indicate hydrated mineral detections. He claims that there is not a substantial difference between the concentration of hydrated minerals outside of the Eridania region versus those within the hypothetical Eridania region, and that there are large expanses of plains between hydrated mineral detections within the Eridania region, which would not have been consistent with the presence of a long-lived lake on Mars. Another reason why the Eridania region is so interesting to study is because it's enriched in potassium and thorium, which are radiogenic heat-producing elements. In the map on the top right, we have a map of the potassium weight percent on Mars. Areas that are enriched in potassium are noted in orange and yellow, and regions that are lacking in potassium are noted in purple and blue. These 4 triangles note the main 4 basins of this hypothetical Eridania Sea. As you can see, all 4 triangles fall into a region that is enriched with potassium. Similarly, underneath this graph, we have a plot of thorium in parts per million on Mars. Areas that are enriched in thorium are noted in orange and yellow, and areas that are lacking thorium are noted in more purple and blue. Once again, these 4 triangles that note the Eridania region fall within an area that is enriched in thorium. OSHA et al. Also conducted a student's t-test to ensure that these regions were actually anomalously enriched with these radiogenic elements, and found that, in fact, um, the Eridania region falls within areas that denote an enrichment of both potassium and of thorium. Because of the heat that could have been produced through the decay of potassium and thorium within the region, OSHA et al. Were able to calculate a crustal heat flow of the Eridania region that could have surpassed 45 milliwatts per meter squared, potentially even more than 65 milliwatts per meter squared, depending on the mantle heat flow during the Noachian. And this would have allowed temperatures at shallow depths that would have supported the formation of minerals like serpentine. With all this information in mind and the contested formation and environment of the Eridania region, we sought to detect hydrothermal mineral alteration throughout the Eridania Basin in order to better characterize the formation environment of the region. The main instrument whose data we used to analyze for this project was the Compact Reconnaissance Imaging Spectrometer for Mars, or CRISM instrument. This instrument has detectors in visible, infrared, and near infrared wavelengths with 430 different band measurements. Each of the pixels within a CRISM image represents 18.4 meters at a 300-kilometer altitude. And here you can see an illustration of what the CRISM instrument looks like in orbit. In order to analyze these images, we begin by downloading the CRISM images. They are open source, and if you wanted to, you would also be able to download them. We then use ND software to apply an atmospheric correction to account for the carbon dioxide atmosphere that Mars currently has. To account for the curvature of the planet, we then map project these images. To further reduce the amount of noise that these images have, we run them through a custom MATLAB algorithm, which divides each pixel by the mean pixel value within each column. We then use these ratioed images to extract interesting spectra from regions that may be of note and potentially contain hydrated minerals. Finally, we're able to classify the different minerals within our CRISM images to potentially serpentine or other hydrated minerals by comparing the samples from these Martian CRISM images to actual lab spectra. Specifically, we analyze CRISM images and utilize reflectance spectroscopy to identify serpentine and other hydrated minerals within CRISM images in the Eridania region. So far, we've analyzed 193 images of the approximately 400 high-resolution CRISM images within the region. Of these 193 images, 64 appear to contain hydrated mineralogy, including some potential detections of serpentine. In this map on the right, we have the Eridania region and different detections of hydrated minerals. In black, we have the hydrated minerals that were identified by Mikulski et al. In 2017. In blue, we have probable detections of serpentine. In red, we have potential detections of serpentine. And in green, we have other hydrated minerals that we have detected throughout the region. Many of the detections of hydrated mineralogy occurred within knobby terrain. So in this high-rise image, you can see the knobby terrain here. It is potentially indicative of uplift, which means that the mineralogy that we may have detected within these knobby terrain features would have actually formed within the subsurface. Here you can see a zoomed in version of just one of these features where you can see how it looks like it may have been uplifted terrain that would have actually formed within the subsurface. Now we can actually get into showing you some of the spectra that we were able to extract from the CRISM images that contain hydrothermal minerals. Here we have a detection of probable serpentine. An image was considered to include probable serpentine if the reflectance spectra clearly contain the representative 1.93 micron, 2.315 micron, and 2.51 micron absorption bands. Here we have two different lab spectra of serpentine in orange and black. These spectra clearly contain absorption bands at 1.93 microns, 2.315 microns, and 2.51 microns. The 1.93 micron band is indicative of the bound water, and the 2.315 micron band is indicative of the magnesium hydroxide bond. As you can see, our blue spectra is the CRISM image that we found and the spectra that we were able to extract from it. You can see that it clearly has the 1.93 absorption band, the 2.315 absorption band, and the 2.51 absorption band. Because all three different bands were clearly present within the spectra, it was classified as probable serpentine. Other images did not contain serpentine, but still contained hydrated mineralogy. Because the 1.93 micron band is indicative of bound water, the images that contain this 1.93 micron band were said to contain hydrated mineralogy. Some of them even contain that 2.315 micron band, which is the magnesium hydroxide band, but definitely do not contain the 2.51 micron absorption band, which is characteristic of serpentine. So once again, we have our lab spectra noted in orange and black here for serpentine, but in blue, we have the spectra extracted from a chrism image, which we have just classified as hydrated mineralogy. So it does contain that 1.93 micron absorption band. It might even contain the 2.315 micron absorption band, but it definitely does not contain the 2.51 micron absorption band. And so this spectrum may be representative of a magnesium phyllosilicate, but not serpentine. If we recall our initial debate in the formation and environment of the Eridania region, Leverington had claimed that the Eridania region could have formed from dry volcanism because the concentration of hydrated mineralogy within the Eridania region, which is denoted by this white dashed line, is not substantially different than the concentration of hydrated mineralogy found in the surrounding area outside of the Eridania region. He had used this as evidence to support the theory that the dry volcanism had formed the Eridania Basin, and not that the Eridania Basin was once an ice-covered sea. However, my research compounds upon previous research of other planetary scientists that have detected hydrated minerals throughout the Eridania region. Increasingly, the detections are becoming less modest in geographic extent, and the areas that contain unaltered minerals are shrinking. This is helping to support evidence that the Eridania region was once an ice-covered sea and was not formed as dry volcanism, as it directly confronts Leverington's claim that there was not a substantial difference in the concentration of hydrated mineralogy inside the Eridania region as opposed to outside the Eridania region. We will continue to analyze the remaining approximately 200 high-resolution chrism images that are found within the region, and we'll likely be able to find additional detections of hydrated mineralogy within the Eridania region, further supporting the theory that the Eridania region was once an ice-covered sea and was not formed through dry volcanism. In conclusion, detections of serpentine and hydrated minerals throughout the Eridania region support the theory that the region was once an ice-covered sea in a hydrothermal system, not formed through dry volcanism. Additionally, because serpentinization produces hydrogen gas, which certain microbes are able to use metabolically, this has some really interesting implications for astrobiology, which we'll discuss in just a minute. Furthermore, chemical remnant magnetization that's observed within the Eridania region might have been influenced by serpentinization, since serpentine produces magnetite as a byproduct of the process. The implications for habitability within the Eridania region are also extremely interesting to study in the context of a hydrothermal system and serpentinization. The conditions, chemistry, and mineralogy of a hydrothermal system, especially one experiencing serpentinization, could have potentially been related to the origin of life. There are microbial communities on Earth that thrive off of only the products of serpentinization because H2 gas is produced as a byproduct of serpentinization. This H2 gas is able to be exploited metabolically by certain microbes, and so they're able to survive only off of the water, heat, and H2 gas that is produced within this hydrothermal system and serpentinization. Furthermore, serpentinization creates a reducing environment, which can cause the precipitation of sulfides. And so regions that had a lot of serpentine might have been hot zones for ancient chemolithotrophic life, because not only would H2 gas have been produced as a byproduct of serpentinization, but also SO4 from radiolysis of within these sulfide-rich zones. And so these microbes might have potentially had two different gases that they could have metabolically exploited, in addition to the water and heat that would have been present within the region as well. In conclusion, we were able to detect serpentine and hydrated mineralogy throughout the Eridania region. These detections support the formation environment of the region as an ice-covered lake and hydrothermal system instead of dry volcanism, as we've increased the number of concentrations of hydrated mineralogy detections within the Eridania region. Furthermore, serpentinization potentially provided the conditions and products that would have allowed microbes to survive. Additionally, serpentine might have also been able to contribute to chemical remnant magnetization that's observed within the Eridania region through the production of magnetite as a byproduct. We are still working to increase the scope of the project by analyzing all 400 images within the Eridania region for hydrothermal mineral alteration to increase the number of hydrated mineral detections within the Eridania region and further constrain the formation environment. Thank you so much for watching my talk. And please feel free to contact me at lucia.bellino@rutgers.edu with any further questions. Thank you so much.